Question number 1. A student prepares 100 milliliters of a saturated solution of MgF2 by adding 0.5 grams of solid MgF2 to 100 milliliters of distilled water at 25 degrees Celsius and stirring until no more solid dissolves. Assume that the volume of the undissolved MgF2 is negligibly small. The saturated solution is analyzed and it is determined that F- concentration in the solution is 2.4 times 10 to the negative third molarity. A1. Write the chemical equation for the dissolving of solid MgF2 in water. So first you have your MgF2 solid, which completely dissociates into Mg2 plus ion plus F minus ion. And then you have to balance it since you have two fluorine, so you have to put 2 here.
Okay. Number 2. Calculate the number of moles of MgF2 that dissolve. So here we start out with 0.5 grams of MgF2, and then we can just use stoichiometry to find out the moles. Okay, so you start out with 0.5 grams of MgF2. So then you do your stoichiometry, and then the molar mass is 62.285 grams of MgF2, and then that is equivalent to 1 mole of MgF2. So, sorry, let me just say it. Okay. And then whenever you multiply everything out, you should get 8.0 times 10 to the negative third moles of MgF2 that dissolves.
Okay, A3. Determine the value of the solubility product constant, KSP, for MgF2 at 25 degrees Celsius. So first, to solve for the KSP, you have to write your formula. And it's products over reactants, but since your MgF2 is a solid, you don't include it. So it's the concentration of Mg2 plus times F minus squared, since you have a 2 over here. Your F minus is your concentration for your F minus is given 2.4 times 10 to the negative third. So we'll write that down. But since the mole ratio of F minus to Mg2 plus is 1 to 2, you divide the concentration of F minus by 2 for your Mg2 plus. So that would be 1.2 times 10 to the negative third. Oh, and for the F minus, you should square it. Sorry. For F minus, you should square it. And then you should get 6.9 times 10 to the negative 9th as your KSP.
Okay, B. A beaker contains 500 milliliters of a solution in which both Ca2 plus ions and Ba2 plus ions are present at a concentration of 0.1 molarity at 25 degrees Celsius. A student intends to separate the ions by adding 0.2 molar NaF solution 1 drop at a time from a burette. At 25 degrees Celsius, the value of KSP for CaF2 is 3.5 times 10 to the negative 11. The value of KSP for BaF2 is 1.8 times 10 to the negative 6. Okay, so for B, number 1, it says which salt will precipitate first, CaF2 or BaF2? Justify your answer. So whenever you're looking at this one, a simple way to do this is just look at, try to find which one has the smallest KSP value. So since this is 10 to the negative 11, that's a lot smaller than this one. So CaF will be your, that will precipitate first. And then just whenever it asks you to justify your answer, all you really have to say is because CaF2 has a smaller KSP value. So I'll just write that.
Okay, B2. Calculate the minimum concentration of F- necessary to initiate precipitation of the salt selected in part B1. So first we should write down our formula, which is Ca2 plus times F- squared equals the KSP. Since we know what the concentration of Ca2 plus is, which is 0.1 molar, we can write that down. So that's 0.1. And then here for the F-, since we don't know what the F- is, and that's what we're trying to solve for, we can write x squared. And the KSP for CaF2 is 3.5 times 10 to the negative 11th. So you divide by 0.1. So that'd be x squared equals 3.5 times 10 to the negative 11th divided by 0.1, and you take the square root of the whole thing. X should equal 1.9 times 10 to the negative 5th. M, concentration.
Okay, B3. So here we're trying to calculate the minimum volume of 0.2 molar NaF that must be added to the beaker to initiate precipitation of the salt selected in part B1. So here we have to take this number, we have to take this number, which is the molar concentration, and we have to, we're trying to find the moles. So, and we know the liters also. So we can set up an equation. Up here it says 500 milliliters, so we know that we have 0.5 liters here. So once we have this equation, we can solve for x, and then we do this by cross-multiplying like that. So your x mole should be 9.5 times 10 to the negative 6. And then this is your moles needed. So from this, we can make another equation. In the equation right here, we see that we have 0.2 molar NaF. So we take that, and then we set it equal to moles over liters again. So we take this amount of moles. And then we put that over x liters, because that's what we're solving for. So once we solve, we can multiply it like this. So you get 0.2 x, which is your x amount of liters, which you don't know, is equal to 9.5 times 10 to the negative 6 moles. And then we divide by 0.2 on both sides. And then we get x equals 4.75 times 10 to the negative 5th liters, and that should be your minimum volume.
Okay, letter C. There are several ways to dissolve salts that have limited solubility. Describe one procedure to redissolve the precipitate formed in part B. So there are many ways to do this, but some of the ways you can do this is by adding distilled water, or heating it if it's endothermic. You can also crush it or stir it.